Good morning, everyone. Once again, it's Aamir Hussain for Jesus and Mary Academy with the sixth lecture of chapter solution in front of you. So, today we are going to see a very important law called Rolle's law. So, it can even come in your exam, it can even come for 1 marks, 2 marks, or even for 5 marks if the derivation is asked. So, today we are going to see the Rolle's law. It was given by F.M. Rawls in 1886 put forward the following result called Rawls' law as. So he has said in a solution the vapor pressure of component at a given temperature is equals to mole fraction of that component in solution multiplied by vapor pressure of that component in pure state. So we have to focus on main things, that vapor pressure of compound at a given temperature, vapor pressure of compound, vapor pressure of a compound. So if there is a compound, its vapor pressure is equals to what? Is equals to mole fraction of that component, mole fraction of that component, vapor pressure of a component, sorry, that is not compound, component, vapor pressure of a component is equals to mole fraction of that component in solution multiply by vapor pressure of that component in pure state. So what is the meaning of a vapor pressure of that component in solution and in pure state? In solution means it is mixed with the solute, it is mixed with the solute. But when I talk about in pure state, it means that is not in solution, but in pure state when we will take the, when we boil that liquid, then we get the vapor pressure from that, and in solution we'll get the vapor pressure little bit different from the vapor pressure we get in the pure state. So there is a formula. Suppose we are going to get the vapor pressure of solute, vapor pressure of component is here now of solution. So here we'll go vapor pressure of solute in solution. So let the vapor pressure of solute be A in solution. Pa is equals to mole fraction of A into vapor pressure of that component, that solute A in pure state. So Pa is equals to Xa into P naught A. That is the formula. Same way, if it is solvent B, we called it B, then Pb is equals to what? Xb into P naught B. What is Pa? What is Pb? So Pa and Pb are the vapor pressure of that component in solution, and P naught A and P naught B are the vapor pressure of that component in pure state. What is Xa and Xb? Xa and Xb are the mole fraction of that component. So we have where A and B are mixture of two miscible volatile liquid. Miscible means they can mix. Miscible word is used for two liquids. If it is two liquids are getting mixed with one another, word miscible is used. If solid is there, we use soluble or volatile. So miscible volatile liquids, where A and B are mixture of two miscible volatile liquids having mole fraction Xa and Xb, and their partial vapor pressure are Pa and Pb. So their partial vapor pressure are Pa and Pb, and vapor pressure in pure state are P naught A and P naught B. Next, if P is the total pressure of the system, if we consider P is the total pressure of the system at same temperature, then by Dalton's law of partial pressure, what Dalton's law of partial pressure say, that total pressure of the mixture is equals to sum of the partial pressure of the mixture. So if P is the total pressure of the system, then if we have the partial pressure A of component A and partial vapor pressure B of component B, then what we will have? So partial vapor pressure of A plus partial vapor pressure of B is equals to total vapor pressure P. Then apply the value of Pa is equals to Xa into P naught A. Same for Pb. Pb is equals to Xb into P naught B. So P equals to Xa P naught A plus Xb P naught B. Then in further, so can we take in place of X, as we know that sum of mole fraction of solute plus mole fraction of solvent is equals to 1. So can we take that Xa is equals to what? 1 minus Xb. So can we use in place of Xa 1 minus Xb? So In place of XA we can use 1 minus XB. Same thing is used here. In place of XA, 1 minus XB is used into P naught A plus XB P naught B. Next, when we will multiply it with this, what we'll get? One step is missing here. So finally what we'll get? That P naught A minus P naught A XB. So we have P naught B XB. So XB can be common. So what we can take? P naught B minus P naught A XB in common plus P naught A this one plus P naught A. So we have got the third equation we can consider in terms of equation also. Okay. Since P naught A and P naught B are constant, so the value of P naught A, vapor pressure in pure state of P and P naught A is considered as P naught A and P naught B are constant at particular temperature. Then from equation third we see that total vapor pressure is what? P naught A and P naught B is a linear function of mole function. So total vapor pressure of any system depends on what? That is a mole fraction. Why? Because P naught A and P naught B is constant at constant temperature. So therefore, at constant or certain at particular temperature, therefore the total vapor pressure, that is the total vapor pressure, is the linear function of what? That is the mole fraction, XA or XB. Okay. So therefore it is said linear function of mole fraction XB. As we are taking here XB, so we are taking XB. If we take XB 1 minus XA, then we consider XA. So therefore it is said that total vapor pressure is a linear function of what? Mole fraction XB or XA. If we take XA equals to 1 minus XB. Thus, again I am repeating, since P naught A and P naught B are constant at particular temperature, from equation third, that this one is the equation third, we see that total vapor pressure is a linear function of mole fraction XB. If we take XA, then it will be XA. When XA is taken, XA equals to 1 minus XB. Thus, a straight line is obtained when pressure is P is plotted against XA and XB. So, if we will plot the graph against total vapor pressure, so we will get a straight line with whom? With the mole fraction. As P naught A and P naught B are constant at certain particular temperature, so the total vapor pressure will be the linear function of mole fraction, which you have to keep in mind. Now we will see it with the help of a curve. There is a curve for Raoult's law, the relationship between vapor pressure and mole fraction of an ideal solution at constant temperature. So it is showing the relationship between the mole fraction of B and the total vapor pressure. We considering at vapor pressure here. So relationship between vapor pressure and mole fraction. So this curve show if there is a ideal gas. So for ideal gas, what we see, we get a straight line. So this is for the total vapor pressure P is equals to what? Partial pressure of A plus partial pressure of B. So it is considered that for XA equals to 1, that time the XB mole fraction of B will be 0. So in that case we get the curve for XA. So for what we'll get for XA, we get a straight line. So for XA we get a straight line. So this point this shows the combination of the two. Same way if we consider XB, we get a straight line, just opposite way. It is shown XA when equals to 0, XB will be 1. When XA is 1, XB will be 0. It is considered. So therefore for XB the value of PA is equals to XA into P naught B. Same way for that is A. For XA, for XB, the value will be PA is equal to XA into P naught A. The straight line is obtained. Same way, if we consider the XB, we get the PB into XB into P naught B, the curve. So, so we have got the two plots which is showing the straight line. When we combine these two lines, we get where they are getting ended, we just draw a straight line which gives the plot of total pressure of the mixture. So from the partial pressure, that showing the mole fraction of A, giving a straight line with the with its vapor pressure, same way partial pressure of B, it also give the straight line. So where they cut it, where they get ended, touching the vapor pressure line, we draw a line. So that also gives a straight line. So that is the line of total vapor pressure of the mixture. That is a P is equals to PA plus PV. So it shows the relationship between what? So the relationship between vapor pressure and mole fraction of an ideal solution at constant temperature. The broken line 1 and 2, we have the broken line 1 and 2 here. The broken line 1 and 2 give plot of a partial pressure, so it gives the partial pressure A and partial pressure P curve. Plot of partial pressure versus composition of solid line 3 shows what? Total vapor, total pressure versus mole fraction. Total pressure versus mole fraction. So this complete line, bold line, shows that shown with the third with the Roman here. So solid line represent total vapor pressure, while the broken lines first and two shows what? The partial vapor pressure, the partial pressure. So where xa is equals to 1, xa is equals to 1, that is liquid in pure, that is the liquid pure A. xa is equals to 1, that is liquid pure. So in that case P is equals to what? If xa equals to 1, then what will the equation? So for xa equals to 1, P is equals to P naught A. And when xb equals to 1, we consider xb, we have taken xb equals to 1. We have taken in the curve xb equals to 1. Here we have taken xb equals to 1. In that case, what we'll see? That when xb equals to 1, that is liquid is pure B. So in that case, P is equals to what? P naught B. At any value of xb, the value of total pressure is given by equation third. So from, if you want to get the value of xb, you have to follow the equation third, which we have done the last page. Now we have the conclusion. That was the Raoult's law for volatile solute. Conclusion from Raoult's law. First conclusion, Raoult's law is applicable only if two components, volatile liquids, form a solution, homogeneous mixture. Not applicable for two liquids which are not completely miscible. So Raoult's law is only applicable when the two liquids are miscible. If it will be not miscible, then the two liquids which are not completely miscible, then Raoult's law will not be applicable. So the condition is that two liquids should be miscible, they should be mixing in each other. Second, liquid pairs which obeys Raoult's law are called ideal solution. So the liquid pair which obeys Raoult's law are called ideal solutions. Such pair are limited, so they are very less. So what are such ideal solution example? Such liquid pairs. So benzene plus toluene shows ideal solution like behavior. Hexane plus heptane shows ideal behavior, obeys Raoult's law. Chlorobenzene plus bromobenzene shows ideal behavior, follows Raoult's law. Third point, the composition of vapor phase in equilibrium with the solution can be calculated from the partial pressure of two components. So the composition of vapor pressure, what is the composition of vapor pressure? How much vapor pressure is there in equilibrium with the solution can be calculated from whom? From the partial pressure of the two components. So if we know the partial pressure of the component, we can get the total pressure or the composition of vapor pressure in equilibrium. If Ya and Yb are mole fraction, Ya and Yb, it's better that it will be Xa and Xb. Xa, it will be Xa, Xa, Xa. So if Xa and Xb are mole fraction of component A and B in vapor phase, then what we have? The mole fraction of A is equals to partial pressure of A divided by partial pressure of A plus partial pressure of B. Instead, we can even write that mole fraction of partial pressure, mole fraction of A is equals to partial pressure of A divided by P total, because that is the combination of all. Same way, if it is XB, we can write PB divided by PA plus PB. So if it is number of moles, we are using number of moles, we apply the number of moles. But here we have to see the partial pressure. So we are applying the partial pressure is given in question. So we can use partial pressure value to get the mole fraction. So same way PB divided by P total will be the formula. So finally we have that PA is equals to what? PA is equals to XA into P total, and same way PB is equals to XB into P total. That is the final formula for Raoult's law for volatile solute. In general, for solution containing number of volatile component, that is liquid, so we can apply the formula Pi component is equals to Xi into P total, same thing. So we have completed the Raoult's law for volatile solute. Now we are going to see one more point, then we'll go with the Raoult's law for non-volatile solute. Now fourth point of conclusion. So fourth point of conclusion is depending upon vapor pressure of pure component, total vapor pressure over the solution may increase or decrease in mole fraction of a component. So it is saying that depending upon vapor pressure of pure component, total vapor pressure of solution can be more, can be less. So pure component have fixed vapor pressure, but when it is in solution, we are getting the vapor pressure of component in solution. So in that case, their vapor pressure may vary. The value of total vapor pressure may vary. It may increase, it may decrease in mole fraction of a component. So as shown in equation 3, the slope upward from left to right, but slope downward from right to left. So what we have seen, that one slope is going from left to right upward, but from right side it shows from top bottom to top. A straight line is drawn from left to right. So same thing is explained here also. So by this way we have completed the conclusion of Raoult's law for volatile solute, liquid in liquid. Now we are proceeding towards the another Raoult's law for non-volatile solute. Let's see. Vapor pressure of solution of solid in liquid. Prior it was vapor pressure of solution in liquid in liquid. Now we have the vapor pressure of solution in solid in liquid. And Raoult's law for non-volatile solute. Raoult's law for non-volatile means the solute which you are mixing in liquid will not be soluble. That will not be volatile. That is the meaning. So that is the second type of Raoult's law for non-volatile solute. What is will be here? Solid in liquid. In Raoult's law for volatile solute, it was liquid in liquid. Now, as solid solute are non-volatile, we see the effect of adding such solute on vapor pressure of a liquid solvent. So here we are going to see what will be the effect when we add the non-volatile solute, and what will the impact on vapor pressure of liquid solvent. So let's see with the help of diagram we have. So in first case we are going to see effect of adding a non-volatile solute on vapor pressure of liquid solvent. So first case, vapor pressure of pure solvent. So if there is no any solute mixed, if they are in pure, if it is pure solvent and vapors are produced from the pure solvent, what we are seeing that the initial level of pure solvent was this, liquid solvent was this, but final level has decreased from here to here, and the more vapor pressures are formed, vapor pressure is there. Initial level, final level is here. So second case, what we are saying that for solution, vapor pressure of solution in which non-volatile solute is mixed, then what we see that initial level is this, but final level has decreased less, means less vapor pressure has produced, less less solvent is consumed, and less vapor is produced. When after mixing the non-volatile solute. So therefore it is observed that presence of non-volatile solute reduces the escaping tendency of solvent molecules into vapor phase. So what we have observed, that presence of non-volatile solute reduces escaping tendency, means formation of vapors, tendency of solvent molecules into vapor phase. So it will decrease when non-volatile solute is mixed. But we have seen that if in pure state you get more vapor pressure, but when the non-volatile solute is mixed, vapor pressure, the vapor gets decreased. So because some solute particles occupy the position of solvent molecule on liquid surface, thus lowering vapor pressure of solvent. So why this happens? Because if there is solute molecules, non-volatile solute molecules, they comes on the surface. When they comes on the surface, they do not allow the solvent molecules to escape out from their liquid portion to the outer portion to form the vapors. So that minimizes the formation of vapor when the non-volatile solute is mixed. Why? Because they occupy the upper position, and when they occupy the upper position, they will not allow the not allow means few of the vapors can pass, but few of them gets inside only. Therefore, it allow very less particles to escape. So, because some solute particles occupy the position of solvent molecules on a liquid surface, thus lowering vapor pressure of the solvent. Now, we are coming to the basic definition and the formula. Rod's law for solution of solid in liquid, that is non-volatile solutes. So quantitatively, the effect of adding a solid non-volatile solute on lowering of vapor pressure can be derived by Rod's law. So Rod's law has derived a equation, a formula to get the position when we add the solid solute, non-volatile solute, how the vapor pressure gets lower. So let's have the definition of for non-volatile solute. Vapor pressure of solvent in solution is equals to mole fraction of solvent in solution into vapor pressure of pure solvent. So the same way as we have in the for volatile solute, XA PA is equals to XA into P naught A. Same way vapor pressure of solution here also. So if solute is non-volatile and non-electrolyte, so the case is that if the solute is non-volatile and non-electrolyte, then this will be the case that vapor pressure of solvent. There we are using in volatile solute solution. Vapor pressure of solvent, because solute is non-volatile, that is not going to form the vapor, that is in solid state. So vapor pressure will be formed only because of solvent, not because of solute. So therefore, vapor pressure of solvent in solution, instead of solution, we are using solvent. Vapor pressure of solvent in solution is equals to what? Mole fraction of solvent in solution into vapor pressure of pure solvent. Same way. So it will not contribute to the total vapor pressure. If the solute is non-volatile, it will not contribute to the total vapor pressure. Vapor pressure will be formed only because of the solvent, not because of the solute. Why? Because solute is non-volatile. Then therefore vapor pressure of solution, if we consider the vapor pressure of solution, then what we have to take? That will be equals to vapor pressure of solvent in solution, because the solution only have the vapor pressure because of solvent only. So therefore vapor pressure of solution is equals to vapor pressure of solvent in solution. Now combining equation 1 and 2, suppose we have considered this one as equation 1 and this one as equation 2, this one vapor pressure of solution. So finally what will get? The final formula for Rod's law for non-volatile solute, that vapor pressure of solution is equals to mole fraction of solvent into vapor pressure of solvent in pure state, or vapor pressure of pure solvent. So that gives the final formula. So therefore we use to give the sign vapor pressure of solution with PS, mole fraction of solvent with X1, or vapor pressure of pure solvent with P naught. So that is the sign. So you have to remember it, that vapor pressure of solution PS, vapor pressure of pure solvent P naught. So we have the final formula that vapor pressure of solution PS is equals to mole fraction of solvent X1 into vapor pressure of pure solvent P naught, or X1 equals to PS by P naught. Equation 3 it is considered. Finally, PS is proportional to X1, that is vapor pressure of solution. So vapor pressure of solution will be proportional to what? So that will be proportional to mole fraction of solvent. Why? Because the vapor pressure of pure solvent is considered constant, kept constant. So therefore vapor pressure of solution is directly proportional to mole fraction of solvent in solution. Again we have the plot, we get a straight line for this also. So plot of vapor pressure of solution versus mole fraction of solvent for solution obeying Rolle's law. So we have the plot of vapor pressure of solution. This one is the in y-axis vapor pressure of solution versus mole fraction of solvent for solution. So this is the mole fraction of solvent in solution. What we'll get? We'll get a straight line, because vapor pressure of solution depends on the mole fraction of solvent in solution. So a straight line is obtained. So that we have got the formula. Now we are proceeding towards one more relation. So keep in mind what we have from the Rod's law for non-volatile solute. Ps by P naught. P naught can be taken above. Sometime we see that it is below. It can be taken above. Ps by P naught is equals to X solvent, mole fraction of solvents. So there is a relationship establishing here. Relative lowering of vapor pressure of a solution containing a non-volatile solute is equals to mole fraction of solute in the solution. So again for solute what we'll consider that why the vapor pressure gets lower. So relative lowering of vapor pressure of solution containing what it contains non-volatile solute is equals to what is equals to mole fraction of solute in the solution. So how much non-volatile solute is present, that much relative lowering of vapor pressure will be seen, that much vapor gets lowered. So it depends on relative lowering of vapor pressure when we get the non-volatile solute. It depends on mole fraction of solute in the solution. Quantitatively we can have the equation if the solution contain n1 moles of solute dissolve in n1 moles of solvent, we get mole fraction that is n2, not n1, n2. So if solution contain n2 moles of solute dissolve in n1 mole of solvent, we get the mole fraction of solvent. So what will the mole fraction of solvent? That is x1 is equals to n1 divided by n1 plus n2. Similarly, substituting the value of x1 in equation 3, we have in the back Ps by P naught equals to x1. So in place of x1, Ps by P naught equals to x1. So can we take in place of x1 n1 by n1 plus n2? So that is in place of x1. We have used n1 divided by n1 plus n2. Now substitute. Till here we have learned. So we have seen Ps by P naught is equals to what? Ps by P naught is equals to n1 divided by n1 plus n2, as x1 is equals to n1 by n1 plus n2. Number of mole fraction of solvent is equals to number of moles of solvent divided number of moles of solvent plus number of moles of solute. So subtracting or substituting each side from 1, subtracting each side from 1 we get. So you have to subtract each side with 1. So 1 minus Ps by P naught, 1 minus n1 by n1 plus n2. So we have 1 minus Ps by P naught equals to 1 minus n1 divided by n1 plus n2. So finally we'll get P naught by Ps divided by P naught is equals to n2 by n1 plus n2. So that is called the formula for relative lowering of vapor pressure, that P naught by Ps divided by N2 divided by N1 plus N2. In this equation, P naught minus Ps express lowering of vapor pressure. So we will take P naught minus Ps that express lowering of vapor pressure, and P naught minus Ps by P naught is called relative lowering of vapor pressure. So if anyone asks you what is the lowering of vapor pressure formula, P naught minus Ps. If anyone asks you what is the formula of relative lowering of vapor pressure, so we have P naught minus Ps by P naught is called relative lowering of vapor pressure. What is N2 divided by N1 plus N2 show? It shows mole fraction of solute. So if it is N2 above, then it will be the mole fraction of solute. So Rod's law, a special case, is a special case of Henry's law. So we have the formula Pa equals to P naught A into XA, or Pa equals to, in place of P naught A, as it is constant, we can use Kh into XA. So Henry's law or Rod's law have some common things in total. Now we have one question based on this.